Hello everyone. Welcome to ILTA Physics Online class. Today we are going to study one of the states of motion of an object called equilibrium. Even though today's topic is equilibrium, I actually want to start by explaining some general ideas that we'll use later when we analyze all kinds of two-dimensional motions. So far, we've learned two main ideas: kinematics, which describes how an object moves, and kinetics, which describes the forces that cause that motion. When we combine these two, we get dynamics, the study of motion caused by forces. In today's lesson, we'll first review Newton's second law, which is the most important law for analyzing motion in two dimensions. Then we'll learn about one special kind of motion state called equilibrium. Usually, we divide equilibrium into two types: static equilibrium and dynamic equilibrium. Finally, we'll wrap up by reviewing general methods to analyze different kinds of two-dimensional motion. All right, let's start analyzing two-dimensional motion. Last time, we learned a visual analysis method called the free body diagram to effectively understand the forces acting on an object. A free body diagram shows all the forces acting on a single object as vectors. Then, by adding those vectors together, we can find the net force acting on the object. For example, as shown in the picture on the bottom right, imagine a kid sitting in a toy car being pushed by two friends. In a free body diagram, we represent the object as a single point, and all the forces acting on it are drawn as arrows, vectors starting from that point. Remember that the force vectors always start from the object. Once we have that diagram, we can break the forces into horizontal and vertical components to analyze the net force on the object. Even if the motion happens on an inclined surface, we can still break the forces into directions parallel and perpendicular to the surface. Now here's something important. So far, we've talked about forces, but now let's shift and talk about motion. We said that the purpose of drawing a free body diagram is to visualize and analyze the forces in the horizontal and vertical directions. In simple terms, that means we calculate everything separately along the x-axis and y-axis. The reason we analyze motion separately along these two directions is because, according to Newton's second law, forces in the x direction only affect motion in the x direction, and forces in the y direction only affect motion in the y direction. This is called the property of orthogonality of vectors, though we'll skip the detailed math behind it for now. So, to summarize, we use a free body diagram to split forces into horizontal and vertical directions, and then apply Newton's second law separately for each direction. Because the two directions of a motion are independent of each other, we can analyze any two-dimensional motion as two separate one-dimensional motions, one horizontal and one vertical. That's the key idea we'll use again and again in analyzing 2D motion. Now let's connect this to the field of dynamics, which explains the relationship between force and motion. Remember, kinetics is the study of forces themselves. It explains what forces exist and how they act. Kinematics, on the other hand, ignores the causes of motion and just describes how an object moves in terms of position, velocity, and acceleration. The law that connects these two, forces and motion, is Newton's second law, also known as the law of acceleration. We usually write this law as F equals ma. But we can separate this into two components: forces in the x direction and forces in the y direction. As we said earlier, forces in the x direction cause motion in the x direction only, and forces in the y direction cause motion in the y direction only. So, in words, we can say this: for an object with mass m, the sum of all forces in the x direction, called the net force, causes acceleration in the x direction, called ax. Similarly, the sum of all forces in the y direction causes acceleration in the y direction called yaw. The reason we can think of x and y motion separately is because they are independent from each other. In the example on the right, we drew the free body diagram for the child in the toy car and used it to calculate the net force acting on the car. Then, by using Newton's second law, we can calculate the car's acceleration. This is one of the most important takeaways from today's lesson, so make sure you understand it and remember it well. Now, let's talk about the first kind of motion, equilibrium. An object is said to be in equilibrium when it's either at rest or moving at a constant speed in a straight line. In other words, the acceleration is zero. According to Newton's first law, if no external force acts on an object, it will either remain at rest or move with constant velocity, that is, with zero acceleration. If we think about that in reverse, it means that if an object's acceleration is zero, then the net external force must also be zero. That's what we call equilibrium. There are two types of equilibrium: static equilibrium and dynamic equilibrium. Static equilibrium is when the object is completely at rest. Dynamic equilibrium is when the object moves in a straight line at a constant speed. In both cases, the acceleration is zero. We can also describe equilibrium mathematically. For any two-dimensional motion, we always use Newton's second law, F equals m. But since acceleration equals zero in equilibrium, that means F equals zero as well. So, for both horizontal and vertical directions, the net force must be zero. In an equilibrium state, the acceleration is zero, so the total net forces in x and y directions are also zero. That's really all you need to remember. We'll practice solving actual equilibrium problems in the next lesson. Finally, let's summarize the three general types of motion that we'll deal with in two-dimensional problems. First, an object can be at rest. Even though it's not moving, that's still a state of motion which velocity equals zero. Since velocity is zero, acceleration is also zero. That's called static equilibrium. By Newton's second law, since acceleration is zero, the net force must also be zero, both in the x and y directions. Second, an object can be moving at constant velocity. That means it has motion but no acceleration. That's dynamic equilibrium. Just like in static equilibrium, the net force in each direction must be zero since acceleration is zero. So for both static and dynamic equilibrium, the key idea is that acceleration is zero, and the vector sum of all forces in each direction is zero. The third case is when the motion is accelerated motion. In this case, either the speed or the direction, or both, may change over time. That means both velocity and acceleration are non-zero. Even here, we still use Newton's second law, F equals ma, and analyze separately in the x and y directions. The only difference is that acceleration now has a value, ix or y, depending on the direction. So the sums of net force in each direction also have values, not zero. We'll study this more closely in the next class using specific two-dimensional examples. That's it for today's lesson. It looks like our learning is also accelerating. We are definitely in an accelerated motion state now. Great work, everyone. See you next time.